type of eclectic style music because that's just the way it is right now. So we've made some enhancements to the design. Needless to say, certain things have happened between the last couple of nights and tonight. Working behind the scenes, of course. Always trying to make things better, right? Is that what life is all about? So if I go to my pictures, I got some websites pulled up. LW, Stonebridge. Survive the night, as they say. Yes, my music is a bit loud and I want it loud. I'm jamming. Oh, you know what? I'm gonna fix that clock too. Good today. I was supposed to work today and I had to call in. I just could not do it. Things happen, you know. Let me go to my website streams here and just make sure that everything is kosher. So the topic of discussion is doing things the hard way, which is typical of my life. But what are you gonna do? Okay, so we've got this picture. We have an LED. Now normally LEDs are operated in the forward bias mode. That means the current travels in the direction of the arrow. But me? No! We don't want to have it go in the right direction. No! We're gonna have it go in my direction. Yo! Can you hear me now? I love my shit. So it's like 1.5 volts, 2 volts, whatever. When you put the 500 ohm resistor in series with the LED and it lights up. So what I'll do, you have to forgive me because I can't see very well. I'm going to go over to my website here, this one, which is not showing up for some reason. Bear with me, we'll get it here soon enough. So first we'll talk about photodiodes and solar cells, and then we will go ahead and change the music. I will lighten it up a little bit here. You have LEDs in reverse bias, you have photodiodes, you have phototransistors, you have solar cells and such that can pick off light energy and convert it into electrical energy. If we do not get this project solved, the project is dead. It won't work. While spectrum analysis and light viewing is all part of the idea, it doesn't convey the information that we're looking for, although it might. So you've got this PN junction in between the anode and the cathode, and electricity, enough voltage is applied between the anode and the cathode. You get current flow. And if you put positive on the anode, negative on the cathode, I think it's correct, you get this current flow from left to right, and the depletion region increases or whatever, and you get current flow, and the LED lights up. Now, they're not really talking about an LED here. They're talking about something else, but we'll get to that in a moment. So there's a certain amount of current that goes through here, and if we skip down to the bottom of this page here, there's a diagram. This diagram shows you the current going through the diode, depending on which type of mode it's operating in, and what the curves look like. So the forward bias mode on the right hand side is when the LED lights up, and it is also kind of non-linear, so you have to be careful, when you crank up the voltage and stuff. On the far left hand side, we have what's called the breakdown voltage. If the voltage across the diode is reversed such that there's current flowing in the opposite direction, and it's a large enough voltage drop, then all of a sudden this thing will go into a certain mode called breakdown avalanche mode, and if it's left too high or whatever, it may destroy the diode. And so when you put it back in its normal state, it won't run again because the depletion region is messed up. That's FUBAR, beyond repair. So the idea of what I'm working on is using a diode, an LED, in the reverse bias mode, which is this blue section. Now, they're saying that if you operate it in the pink section, it very carefully, you can detect single diodes, okay, or single photons coming through. That's all good and whatever, but we're not in the business of collecting single photons, although that would be a thing to study. We want this thing to operate at a certain current level, and I believe each one of those curves may represent a different voltage level. When you got current and you got voltage, so if the voltage gets more negative, this current will increase. Well, no, actually the current stays the same. So no matter what the voltage, this reverse bias current stays the same. And we believe we've calculated about 3 microamps on one of those LEDs. Now that's a low current. So what we need to do is we need to take that current, we need to amplify it while we're measuring it. But we can't measure the current. We don't want to measure it directly, because now if we go back to my circuit, and we'll look at the circuit here. You've got this resistor that you can put in there. It says 10K pot, but it's actually 2.5 megohms. That's pretty large. And I've been able to drop the resistance down to a point where there's 3 volts across the LED. There's 2.5 volts across the LED, reverse bias. And there's like 7.5 across the resistor, or 6.5, or whatever. The total's 8 volts, not 15. So the voltage drop will change, okay? But what happens is that the voltage drops between the LED and the resistor balance each other out in such a way that the current is remaining the same. I'm assuming maybe that's what it does. They're balancing each other, because they're definitely changing, and they change quite a lot. And so we don't exactly know what the avalanche breakdown voltage is, or exactly even how to measure that. If we can't measure the current directly, we have to measure it indirectly by measuring the voltage across the 200 ohm resistor, 2 mega ohm resistor, and every time we change that, we get a voltage drop, and we can check, shut the circuit off, and we can make a chart and find out, what that information is. They say like after 5 volts, okay, it can go into that region, but most of the people are saying 25 to 30 volts before the LED breaks down. So in a sense, we would probably have to make a chart and find out what those levels are, but I'm not going to do that tonight. What I want to do is I want to get this waveform. So like, I'm thinking that in order to amplify this, we're going to do what's called a whetstone bridge. And so if we have a potentiometer that does the same resistance on both sides, we say it's 3 volts, we already kind of know what that resistance is. It's like 1.5 megohms. Okay, so we could put in 1.5 megohm resistors in series with the LED, in the reverse bias mode, and we can come up with a voltage. And then probably we could use a 100K pot to trim out the voltage. I mean, I don't really know, because then we've got to put voltage on the other side. And then, so what's going to happen when the voltages equal each other on both sides? There will be a split current flow on both sides that go to ground, and there will be no voltage drop across those two dots inside the whetstone bridge. Now, when we change one side on the top, we change that one resistor to change that voltage down here. Now we're going to get a voltage drop, and you know, I'm just not keen into that music tonight. We're going to get a voltage, we may get a voltage drop across the whetstone bridge. Now, you can, most people, I think they put a microammeter in here, and so, you know, maybe that's the thing. I've got tons and tons, I got a crap load of meters. So this is what we're going to do. We're going to build this. We're going to find out, we're going to take some measurements. I know like 3 volts, maybe 4 volts. I'm going to say 3 to 4 volts. You know, that should be a good working voltage. And that will get me 2 current measurements. And, you know, right? So if the current measurement is the same and the voltage is such that, you know, so that's the problem. They said that to take the probe tip across the variable resistor, you know. I'm thinking it's still going to be, the current is still going to be the same, you know, because I mean, it will change, but maybe this is where we can add the AC voltage. So what's going to happen is we add the AC voltage to another LED, and then, because that's right, they didn't tell you what happens to that LED in reverse bias when another LED is turned on next to it, that kind of thing. So that's what we're going to do. Now, it seems as though we can test this. So the other thing is with this web page here, if we try to get back to the web page, normally it sort of looks like an operating mode, like a quiescent point. A Q point is like a point in the middle of the curve where you can put a sine wave and it goes back and forth across the curve before it gets distorted. And so that's the reason for increasing that voltage to the center point of the reverse bias mode to get the maximum amount of headroom or space to amplify the signal that's coming in. That's just a guess. I consider that as an operating point. So like if it's in the middle, you know. So aside from that, then we've got, this is a photodiode, and you know, they're comparing it to solar cells and so on and so forth as far as detecting energy. With the photodiode, it's designed to work in that mode, so you can run it and well, actually no, they got plus on the bottom here. They got plus on the bottom, so I don't know how it gets its ground, unless if it gets the ground right through the op amp, because that's generally a thing. It goes plus minus, and back here it goes reverse bias and so on and so forth. The light comes in and it gets amplified. So in the photodiode, if light comes in and there's an amplification factor, we must assume that there's an amplification factor for, you know. But as far as the solar cell, like, I don't really know, you know, what's going on with that. And there's another circuit here. This is an LF351 JFET input op amp. Some of these op amps are pretty good, but still, you know, we're going to use discrete components. Photodiodes characteristics. So you see this lines represent, they're similar to the LEDs in reverse bias, right? Well, I did mention solar cell. They don't probably really give you. There's photo transistors too, and I don't know. Like, I think I have some, but I don't really know. These are all different light detectors. Now, the photoresistor, its response time is very slow, so you wouldn't get information off of it. And so I was looking up the 2N2819, okay? And so this is what this AI said. 2819 is an obsolete NPN silicon power transistor. This goes to prove to you, beyond a shadow of a doubt, that you do not read everything as truth on the internet. The AI is freaking stupid, all right? Whatever come up with this information or however, I don't know, all right? But then this other AI over here got it right and said it's an obsolete N-channel JFET, which is a junction field effect transistor, which is very, very sensitive, has high input impedance, and very good to pick off static electricity in the room, which is something that I designed for. And it has an equivalent of 2N4416. My schematic program didn't have the 2819, but it had the 4416. So we're going to look at the comparison between the 4416 and the 2819. And I think I know who that is, but just bear with me. Uh-oh. Oh, she sent me a song. Well, okay. That's nice. And what I'm looking for in the spec sheet, I don't necessarily care about gain. I'm looking for max operating voltages. There's a gate source voltage of -6 volts. You'll see a typical gate reverse current saturation breakdown voltage, gate source cutoff. I'm talking 15 volts here. So they're acting like that's a supply voltage, I think. Common source for transconductance. Drain source, 15 volts. Gate source, 0 volts. And you've got 100 megahertz to 400 megahertz. We're going to be operating less than 100 megahertz. Common source power gain. Typical values if for design aid only, not guaranteed, etc. Transfer. On resistance drain current. A gain, there's a gain here. So we've got voltage gain with the drain current down at the bottom. So it has a high voltage gain with a very low drain current. But there's gate leakage, there's all kinds of stuff here. That's what it looks like. It's got the arrow pointing in, and you got the drain and the source. And it shows you, the other diagram shows it. Oh, here's what I'm looking for right here. So they got minus 30 volts, minus 35 volts gate current, 10 milliamps. These are like max ratings. So you don't want more than 10 milliamps of current flowing through there. And we're in a range of microamps, so there's not have to worry about that. We've got a storage temperature. These are 300 milliwatts. And the operating junction temperature operates minus 55 to 150. That's pretty good. Now it says D rate 2.5 milliwatts per degree C above. And so it doesn't say anything about below. So let's go ahead and go to the 2819 and see what. So we've got drain gate voltage. We got 25 volts, 25 volts. So the schematic program is going to, that's 50 milliamps instead of 30, forward gate current, etc. minus 55, 20. Basically, it's the same setup. It's the same setup. Now for 1 kilohertz, it shows minimum, min-max, forward transfer conductance. It's like a gain thing. 2000 to 6500. Let's see if that has that value. Common source input susceptance. Forward transconductance is about 4,000. Okay, so like they're similar enough, and these are higher frequencies. Like this goes up to 100 megahertz. This one here, they're talking 1 kilohertz. I've got the 2819. Okay, the computer program does not have that. So that's that particular story. So I'm going to get rid of, I'll just drop this out for now. And then we're going to go to the circuit program. And we're going to see if we can drum up. That's the a-holes lighting out their damn firecrackers. So I'm going to try to do a new. I don't need to save it. Oh shit, it changed the fucking values, didn't it? Let me try something. Okay, so what we're going to do is we're going to delete. We're going to use the same, because it changed the settings of the color. I was wondering if it was going to do that because it's POS. But anyway. Yeah, we're going to get rid of Let's just start to delete things here. Actually, so delete that. It says move mirror item. What that means? Duplicate. Okay, so we could duplicate. Oh, I'll have to change that one. Oops, shit. I fucked that up, didn't I? When I move, so view, options, schematic, colors. When I move the item, it's black. Background, schematic background, digital wave display. can't do anything about that, can I? That's the title. Oh, I guess it was down here. If I grab that, I should be able to move it. It doesn't show me where my arrow is, though. It's okay. I'll just do it when we get there. My circuits, for the most part, are small. Okay, so we are going to have a ground. Oh, I see, it's blue. It moves. We've got an AC signal source, and I don't know exactly how I'm going to incorporate that just yet. I'm going to move this. You can barely see that blue. I'm going to duplicate this a few times. So our central point, now let's see, if we add a wire, and down here. Now let me grab this here. I'm going to move this over and down. Change this to yeah, big deal. Well, actually, that one's going to be shut off. That was 500. What is that actually going to be? I don't know what that resistance value is. I know the current. I know the current and a voltage drop. We've got to figure out a resistor value for this, don't we? Yeah, hoop-de-doo, big fucking deal. So we know the current value is 3 we could say 5 microamps, but I would say 3 microamps. We have to determine a resistance. So we've got a voltage of 3 volts. 3 volts divided by 3 microamps. 1, 2, 3 right there. So that's equals. That's a resistance of 1 megohm. Okay. So we change this to a 1. Oh, I did make a mistake up there, didn't I? This is supposed to be a K up here. I should go out and watch the fireworks, take a little break, huh? I'm gonna be doing that all night long. Oh, this is supposed to be 500K. 5. Just hope they don't start a fucking fire. So we've got 1 mega over here. And I'm gonna put in an LED now. So we've got to find a diode. I've got an LED, and we're gonna use that's just red, green, yellow, amber. We use LED 2. Oh, fuck. Where's the LED? Did I put it on there? Oh, something's wrong. Oh, it's this place. Okay, so let me go back to the LED. Go back to here. Now we've got to rotate this. Now I got a wire. So you can hit escape and just that eliminates that. Now I don't know if I can grab this. Okay. Now we're gonna have a junction. No, it's not gonna give me. Let's put. I don't know what to put. I'm supposed to put. Well, it doesn't really matter, I guess. This is supposed to be reverse. Yes, it is. Alright, so put a ground. We're gonna move this. And we're gonna save as. Got some LED stuff saved. LED circuit. So we're gonna call this one number 2. I'm gonna add another wire. So I've got a bridge circuit. No, there's supposed to be percentages here, but I guess not. And we can add an instrument. Multimeter. I'll put the multimeter here. We're gonna measure current. Now the current's gonna be the same, so voltage. AC RMS. There's that one. Now, in order to get the scope to show up, we've got to put an AC signal on here. So let's add a capacitor like we did the other day. They're not giving you the types of capacitors. That. This. You'd think it would snap to the wire, wouldn't you? And then we've got to do another from here. Okay. And it's going to be 1 millivolt. It's supposed to be 1 kilohertz. How do I... Simulation analysis setup. I thought there was an AC waveform. It's AC. We can do 100 hertz to 10 kilohertz. Let's try a linear sweep. Now we're going to do an AC, DC, this is the part that I didn't. File, save. Let's try to run this here. No source specified for AC analysis. Display despite less, not less, no. It's fucking there. Device properties, edit digital edit pin data. What does that do? Edit digital device display data. Edit digital parameters. The only thing left. Digital device not selected. I can't tell it what frequency it's supposed to be. Like, what the fuck? Spice prefix characters. What the fuck just happened here? Yeah, I don't know what to do here. Label value. description, package. This is to be 8 volts. Wait, let me see that again. Fuck. File. Save. Now it's not letting me run the simulation. No source specified for AC analysis. AC linear. No source. Jesus Christ. Oh wait, so I need to do, why doesn't it show me? It's just showing the multimeter. There's no scope down there. That's just DC bias. Oh, that's not right. This is a... Oh, this is a DC source. Would that be a signal generator instrument?